Hello, everyone. I'm excited to welcome you to today's talk, Breaking and Fixing Unreal, an engineer's guide to problem solving. Over the course of this session, I want to take you through the real-world engineering mindset that we use when working with Unreal Engine, particularly when things go wrong. We'll look at how we identify problems, validate them with data, assess risk, and apply practical debugging strategies, all while balancing real production constraints like deadlines, platforms, and in our case, the impact on our clients' projects. This is a talk for anybody who's ever stared down a cryptic crash log, a misbehaving shader, or a regression with no repro steps. It's not just about fixing things, it's about how we approach problems systematically, how we use profiling data to validate our assumptions, and how we build up a culture of resilient, thoughtful engineering. So whether you're deep in the engine, or just want to level up your problem-solving workflow, welcome. Let's dive in. Before we get started, a quick intro. My name is Thomas. I'm a studio director and an Unreal software engineer at Prismatic Studios. We're an Unreal Engine technical consultancy and co-development studio based in Auckland, New Zealand. And we work with clients around the world to solve complex problems in Unreal. Our team has experience across a wide range of domains, from games, tools engineering, to non-games applications like simulations and real-time animation, or even virtual production. We continued our Unreal Engine Gold Service Partner status into 2025, and we work really closely with Epic as a Epic Pro Support Partner, previously UDN. A lot of what I'll be talking about today comes directly from the trenches of that work, the kind of bugs that show up when the pressure before launch has boiled to a maximum, and there is very little time to fix them. So, when I say technical problem solving, I'm talking about more than just fixing bugs. It's the process of understanding, diagnosing, and resolving complex issues, especially when the symptoms are unclear or misleading. It's about using the right tools, asking the right questions, and staying methodical. In Unreal, that means knowing both what the engine is doing and why, and learning how to work with it instead of against it. Over time, I've come to believe that almost every technical issue we deal with in Unreal can be grouped in one of these four broad categories. Firstly, we have implementation and performance issues. These are just your classic bugs or inefficiencies in how systems are built. That includes both things that don't work and things that work poorly, like frame drops, memory leaks, incorrect logic, etc. Then there's engines and system integration. This is where things break between different systems, version upgrades, platform-specific edge cases, or issues caused by third-party SDKs or plugins. These are tricky because they often involve Unreal internals or external factors outside of your own immediate codebase. The third bucket is technical debt and architecture issues. These are the long-term pain points. Maybe you've built something that worked once, but now it's fragile, hard to debug, or impossible to extend. This kind of debt tends to accumulate slowly until it explodes under pressure. And finally, scope creep, where the technical issues arise not from broken code most often, but from shifting requirements. The feature keeps growing, the complexity spirals, and suddenly you're firefighting on all fronts just trying to keep up with what the system now needs to do. So why does it matter which category your problem falls into? Because each type of problem usually involves a different group of people that have to help you solve it. For implementation or performance issues, or anything related to engine and systems integration, you're often working directly with other engineers, reading through their code, checking logs, profiling, stepping through engine source, etc. But when it comes to technical debt or scope creep, solving the problem is only part of the challenge, and the other part is convincing somebody else that it needs to be solved at all. These kinds of problems typically involve conversations with producers, leads, stakeholders, etc., because the solution may require time, refactoring, or rethinking scope. And that's not always visible, unless you can explain that long-term cost to them. So identifying the type of problem early helps set you on the right course, not only technically, but in terms of the team communication and buy-in for resolving that problem. Inevitably, over the course of development, you're going to run into some, if not all, of the problem types on that last slide. And as engineers, problem solving is our bread and butter. But let's be honest, sometimes you hit a problem that just feels overwhelming. There's no clear repro, it's because of somebody else's code, or worse, it only happens sometimes. The key is, when overwhelmed, don't try to solve the entire problem all at once. We need to try and break it down. Get clarity on what we know and what we don't, and what we can test. Narrow the scope of investigation, and attempt to eliminate as many variables as possible. The rest of this talk is all about building that process, how we move from, I have no idea what's going wrong, to, okay, I know what's wrong, and I know how to fix it. So the first step in any problem-solving process is accurately identifying the problem itself. It sounds obvious, but in practice, it's easy to misdiagnose an issue, especially in a complex system like Unreal. If we start fixing the wrong thing, we risk wasting time and introducing new bugs. So once you suspect a problem, your first job is to frame it properly. That means stepping back and asking clear, structured questions to define its scope. Asking questions like, can we reliably reproduce the issue internally? Is it a local, networked, or platform-specific issue? Is it only happening in cooked builds? Is it console only? Does it depend on latency? These sorts of questions. And the question I often find the most useful, what changed recently in the system? New code, config changes, engine upgrades, etc. The answers of these will set you on the right path. So this example comes from a real case that we worked on, assisting a studio trying to track down a shutdown crash in their shipped title. The issue happened during application shutdown, specifically on a background Direct3D thread. And while it didn't affect gameplay, it still impacted crash statistics and the overall perceived stability of the application. The biggest challenge was that the crash wasn't reproducible easily at all. The stack trace pointed to the FD3D12 dynamic RHI system, likely during resource cleanup, but the call stack was partially unsymbolicated, which slowed analysis, and combined with the fact that this seemed timing related, possibly a race condition between the game thread shutdown and the background D3D thread, it was clear that we needed more data before we could move toward a fix. So after looking through the provided dump file and the crash call stack, we worked closely with the engineer to gather more targeted information to isolate the problem. We asked key questions like, when did this start? And we found that the first occurrence began in November 2024, just after upgrading to Unreal Engine 5.3.4. We also explored frequency. The crash was intermittent, ranging from 0 to 2 occurrences per day in most cases, but spiked to 16 instances per day during an intense internal playtest session. And importantly, we ruled out hardware-specific causes. The crash happened across a wide set of configurations, from RTX 2060s to 4080s, and on both discrete and integrated GPUs. So finally, by mapping crash frequency against the upgrade timeline, we pinpointed that the behavior began shortly after the 5.3.4 update, but persisted through 5.3.5, and narrowing the search to this recent engine changes in that window. So since we couldn't easily reproduce the issue, our goal became to work with their team to stress test and validate the shutdown path. We focused on 3 main areas: memory safety, thread lifecycle, and tooling. Firstly, we recommended a review of how the background threads, especially those related to rendering, were being shut down. We wanted to ensure that they were correctly joined or terminated before engine systems or heap memory were being torn down. The crash pointed towards an RTL free heap, which often suggests memory misuse, like double freeze or use after free. So we recommended they audit the memory allocation and destruction patterns in shutdown-related systems, particularly the D3D12 and the RHI. So to support this, we recommended memory profiling tools, enabling ASAN or address sanitizer, and optionally malexstomp to catch otherwise invisible issues. Even though we couldn't reproduce the crash, we could still build validation into the shutdown routines to catch problems as they occurred. To ensure no background threads were still accessing resources after they were destroyed, we recommended that the team introduce thread guards or debug checks to catch any late or unsafe memory access. Through this additional debugging, the team were able to identify that there was indeed an attempt to read an invalid memory address during the shutdown sequence, and they managed to fix that bug. One of the most common mistakes that we see, especially with less experienced teams, is guessing. As developers, we can naturally jump to conclusions based on symptoms rather than evidence. I can't recommend enough that when facing difficult bugs, to validate your own assumptions about the issue, to confirm root causes, and use profiling and debugging tools to get hard evidence so that you're not just fixing what looks wrong, but you're fixing what is wrong. On a recent multi-platform title, we were targeting 90, 60, and 30 FPS depending on the platform. That meant that we had to be really intentional about how we profiled. Using Unreal's profiling tools and platform-specific analyzers, we were able to identify exactly which systems were bottlenecking performance, and more importantly, why. That allowed us to focus our engineering effort where it actually mattered. Without that data, we might have spent days optimizing the wrong thing or missed critical issues entirely. The starting point for pretty much all profiling in Unreal is Unreal Insights, and Unreal Insights helps to identify bottlenecks, which is really useful when optimizing for performance. At a high level, Unreal Insights is a standalone profiling system that integrates with Unreal to collect, analyze, and visualize data emitted by the engine. I think there's actually a very in-depth talk on Unreal Insights potentially tomorrow, so I'd check that out. In addition to providing robust coverage of the engine's existing systems, Unreal Insights makes it easy to add your own profiling data as well. So we added more scoped trace events to drill down into expensive functions and understand their internals. Scoped trace events integrate cleanly into the trace system of Unreal Insights. With just a few macros, we were able to mark up both engine and gameplay code to get a much clearer picture of where that time was going. So to hit target frame rate, firstly we had to figure out what was slow. We needed to identify which areas of the game were causing performance issues. And the go-to tools for that are the console commands stat unit or stat FPS. From there, we profiled those sections more in depth to understand what was taking the most time and whether that time was justified. Remember that it's actually okay for a feature to be expensive as long as it's actually worth it. So using insights to develop a baseline control of various stages of the game, we were able to identify 4 bottlenecks. Budgeting calculations for prioritizing features that were taking measurable time, AI, specifically the AI controller, animation blueprint, control rig, character movement code, which consumed a significant chunk. Some functions we found were slower when the GPU was active, especially on platforms that shared memory between the CPU and GPU. And the physics tick alone was taking almost 4 milliseconds of the frame. The good news was that a lot of things had already been done right in this project. Tick settings were optimized, actors that didn't need to tick weren't ticking, and when we looked at the profiling data, there was no single egregious offender. Nothing stood out as the fix this and you're done kind of win. But that also meant that our challenge was a bit harder. We needed to shave off small amounts of time from many different areas instead of getting a big payoff from a single optimization. To hit our 90 FPS target, we still needed to recover just over 2 milliseconds of frame time. And that's a lot when you're already running lean. So the question became, where can we trim safely without compromising the experience? A common issue we identified in this project was that using blueprint nodes like getComponentByClass often meant repeatedly copying data during a tick. On the surface, it's a convenient node. But under the hood, it creates a new array and copies component pointers into it every time that it's called. So the fix, we moved the logic to C++, retrieved the components once, and used a T-inline component array on the stack to avoid heap allocations. We also began pre-reserving memory for arrays and used T-inline allocators where possible, again, keeping memory on the stack instead of the heap. We also found that we were making multiple calls to has matching gameplay tag, which uses the iGameplay tag asset interface. In Blueprint, each call copied the owned tags container or performed more complicated logic. So instead, we retrieved the tags once, cached them, and then ran the queries against that cache, which resulted in a significant speedup. Using Unreal Insights, we could pinpoint the cost of these functions, but you still have to look into the blueprint node itself to understand what that helper function is actually doing. It's worth noting here that just because you're in Blueprint doesn't mean you can forget about how memory is accessed and used. So with these changes, we reduced the cost of some functions by 80%, and every single of these small wins really adds up when you're trying to maximize your performance. On some of our target platforms, another major factor we discovered during optimization was memory contention. On these systems, there was significant cost to accessing memory that wasn't local to the CPU. For example, shared memory between the CPU and GPU introduced notable latency. This meant that even small memory-related optimizations had really outsized effects on performance. In Insights, we observed a key example, which I've got up on screen. The same function, same code path, same workload, was taking 10 times longer when the GPU thread was active on this hardware. It jumped from 10 nanoseconds to 100 nanoseconds purely due to contention over shared resources. Now, this is one of those optimizations that's easy to overlook, but when you're chasing 1 to 2 milliseconds of frame time, every cache miss matters. So to address this, we started caching frequently accessed values, structs, component arrays, etc. We built structs to pass between functions, keeping relevant data bundled, instead of fetching from various classes each time. Even though many actors had been moved to tick during the physics phase, we still had 1.6 milliseconds of idle time on the game thread waiting to start post-physics work. So we explored 2 options here. We could either move more work into the during physics tick to fill that gap, or reduce the duration of the physics tick itself. Using stat chaos and stat chaos counters, we found some unexpected results here. A level with more physics bodies had a 2.66 millisecond physics tick, and another with fewer bodies had a 4 milliseconds physics tick. So digging deeper using Unreal's physics views, we found complex collisions, objects with large bounds, and static geometry marked as movable. You can quickly find large collision geometry in the content browser pretty easily by searching collision prims greater than or equal to value. In this case, we did 500. And you can run this console command, collision.listObjects with complex collision, with collision complexity, use complex as simple, to find assets set to use high complexity collision data. And once we found these misconfigured assets, we could clean them up. And the assets with unnecessary collision, we were able to reduce the physics tick time to get us within budget. Unreal Insights helped us find and fix dozens of micro issues, none of which were obvious from the outside. By combining smart profiling, blueprint awareness, and C++ optimizations, and memory management, we clawed back the performance we needed 100 nanoseconds at a time. Another useful memory profiling tool that Unreal provides, specifically for memory diagnosis, is memreport. At a high level, memreport captures a snapshot of memory usage in your project at runtime. It shows us what is in memory at that moment in time, assets, engine systems, streaming levels, textures, meshes, audio, etc., all broken down by category, and often by individual object type. You can trigger it just by typing memreport into the console. That works in Pi, standalone, or in a package build. But it's worth noting you probably want to use the -full flag, which gives you a much more detailed breakdown, including things like asset streaming info. It's worth mentioning that this isn't a visual profiler like Unreal Insights. And under the hood, it's pretty much a tool that just runs a bunch of console commands and then groups their output together for you. So it's more of a static report. Epic have actually indicated that they're actively working on additional memory reporting in Unreal Insights. And some aspects of memreport, I believe, are no longer being actively maintained, but it's still a really useful tool for comparing memory usage between builds, checking memory budgets on different platforms, or to identify memory spikes or leaks after specific level loads. A lot of the time, you'll discover that a single class, maybe a uTexture2D or uSkeletal Mesh, is using way more memory than expected, and memreport gives you the exact list of instances that contribute to that. So if you're dealing with memory pressure, unexpected garbage collection hitches, or just doing a memory optimization pass, memreport should definitely be considered as one of the tools in your kit. I'll show you a quick example of what this looked like in action on a recent project we worked on. So this is a real case where memreport helped us isolate a tricky memory crash on a console game. We were running into memory-related crashes throughout a play session, and it was the classic behavior of things would seem fine for a while, and then it would slowly build up, and then it would fall over without a particularly consistent repro. Nothing was really actionable from the call stack, so we turned to memreport to start building a picture of what was actually happening. One of the key things we wanted to look at here was the allocation bins. Essentially, where and how much memory the engine thought that it was using at the time. Since console memory can be really tight and segmented, we enabled larger memory modes in development to get a clearer picture of how much we were using right before the crash. And that let us generate valid memreports just before things would have typically fell over. So we saw that memreport was showing 14 to 15 gigabytes of memory allocated, which was beyond the memory limit of that console. So this was a clear case of over-allocation. From there, we traced it back to an at-the-time experimental engine feature, geometry caches, and that was leaking memory aggressively, in our case, close to 500 megabytes per instance. It became easier to track down these issues once we knew that the issue was due to large allocations. Interestingly, while we were digging, we actually found a memory leak in the engine itself, in the RHI pool allocator. It turned out that this issue was still present all the way until 5.6 preview, so we reported it to Epic and contributed a fix, and it actually made it to the 5.6 release. So this wasn't just a project level win, it was a case where the use of memreport actually helped improve the engine for everyone. The next tool I wanted us to take a quick look at is Pix, which is Microsoft's performance tuning and debugging suite for Windows and Xbox game developers using DirectX 12. Pix is incredibly useful for Unreal developers shipping on Windows or Xbox platforms, especially when you're digging into low-level performance bottlenecks or trying to understand how the GPU and CPU workloads are interacting under the hood. Even though Unreal abstracts a lot of DirectX 12, Pix still gives you a powerful insight into how your content is reaching the hardware, making it essential for deep performance tuning, especially for Xbox and high-end PC. Microsoft Pix is vendor agnostic, which means that it works on all GPUs that are using DirectX 12, and as of Unreal Engine 5.6, it's supported directly via a capture button in the editor, which makes it really easy to start a session. Generally, as a studio, we use Pix as a render debugger, though more often than not recently, we've used it to rule out GPU side issues rather than just debug them. So the case I'm going to show you is how we used PICS to validate a potential nanite performance issue. In typical raster graphics, DDX and DDY instructions are handled by the GPU. But in nanite, this isn't the case. Nanite relies on analytic derivatives wherever possible. So in cases where analytic derivatives are not available, nanite has to render in a 2x2 quad to compute the change required between DDX and DDY. This impacts variable rate shading. And in the process of optimization on this project, we noticed that apart from a very select few number of meshes in our scene, every object in our scene was red when we enabled nanite's no derivative ops advanced view mode. We were close to frame rate target, so it wasn't a critical issue by any means, but it suggested that either the detection system wasn't working on the engine side, but given that that looks for derivative operations directly in the shader bytecode, that hardly seemed reasonable, or we had inadvertently caused nanite to use quad rendering for every draw in the scene, completely eliminating any performance uplift by variable rate shading. So at that point, we wanted to prove two things: that we truly had derivative operations, and the derivative operations were caused by our material graphs. Unreal Engine gives you excellent visualization modes, like in this case, the nanite advanced view modes, that are great for answering the what questions. In this case, we used the no derivative ops view mode, which highlights draws that rely on derivative operations in the material shader. This helped us answer what was happening. Almost every draw in our scene was using derivatives, turning pretty much the entire viewport red. But that only got us part of the picture, because visualization shows us symptoms, but not root causes. So to go deeper and to understand why this was happening, and how derivative instructions were actually being introduced, we turned to PICS. With PICS, we could inspect the shader bytecode ourselves itself, verify the presence of derivative ops, and then trace them back to the material graphs that were causing them. In other words, Unreal told us what was wrong, but PICS told us why. And that's critical when you're trying to optimize at this level of precision. So let's look again at what we see in Editor. On the right is the no derivative ops view that is available from the nanite visualization menu after advanced visualizations has been enabled, which you can do with that console command. We see that in the no derivative ops view that we've caused nanite to use quad rendering for all of those meshes that view red. With PICS, we launched the package development project, and before we capture a frame, we just want to set r.rhi set GPU capture options to 1, which will then export the markers and names we need to track those draws down. So why is the leftmost object using derivative operations, but the center isn't? Well, the answer lies in how that material is actually sampled. Nanite wants to use Texture 2D's sample gradient as it passes in derivatives explicitly, while samplers like Texture 2D's sample bias implicitly calculate their derivatives. An illustration of this can be seen in that PICS capture up there. And my apologies if it's hard to make out, but it doesn't really matter. The gist of what it is saying is that PICS has selected the draw for the m_test triplanar 1 material, which is assigned to that left mesh. And I've selected the world normal gbuffer output to visualize that call. In this case, we care about the shader bound to that call. It's on the compute queue, as the nanite base pass is a compute shader based. So when we investigate the shader itself further, we can see on screen that the calculate pixel material inputs analytic derivatives function for the material using triplanar projection has a call to Texture 2D sample bias. We can then compare that to the material with analytic derivatives, and we can see that it uses Texture 2D sample gradient. This is why our middle object showed up as blue in the nanite no derivatives mode, as the GPU treats Texture 2D sample gradient as a gradient-dependent operation which takes explicit derivatives rather than calculating a bias. So in this example, before we tried to remove derivative operations, we wanted to understand a few things. Firstly, why were they there? Are they serving any visual purpose? But then, how are they getting into the shader? Lastly, what are our alternatives? What we discovered was that the leftmost object used Texture 2D sample bias, the middle object used Texture 2D sample gradient with analytic derivatives, and the rightmost object was using both sample bias and sample gradient on 2 of the materials, causing it to appear somewhat red. This was important as it proved that it was due to our material setup, not a false positive or an engine bug. So this confirmed both the what and the why and gave us confidence to proceed with our optimization. Okay, the last tool I want to quickly touch on is NVIDIA Insight. Insight Aftermath is NVIDIA's GPU crash debugging tool designed to help Windows developers using GeForce GPUs track down what the GPU was doing at the exact moment a crash occurred. It's integrated as a lightweight C++ library and is supported by Unreal Engine, so you can include it in your project with minimal overhead, and it's actually even light enough to ship with your final game builds. What makes Aftermath powerful is that it captures detailed crash dumps from the GPU and supports inserting your own markers into the rendering pipeline, giving you clear breadcrumbs when you're trying to chase down GPU hangs or TDRs, which are notoriously painful to find. While other profiling tools show how your game performs when things are running well, Aftermath, on the other hand, is focused on postmortem debugging, helping you diagnose black screens, device-removed errors, or GPU crashes that are notoriously hard to reproduce. So this is what you'll be presented with when you open up Insights on your PC. As a studio, we most often use this tool to debug GPU crashes using the GPU crash dump inspector. Again, I don't expect you to make it out on screen, it's just an image, which helps us find the root cause of a random GPU crash. So when loading a crash dump into Insight, a good first step is to check the exception summary under the dump info tab. And this section gives you a high-level view of what went wrong. For example, whether the GPU was hung, or if there was a page fault or a shader-related crash. If it turns out to be a memory fault, the next place to look, is kind of where I've highlighted, is the page fault section under the crash info tab. This will help you determine if the crash was due to something like accessing memory that was out of bounds or already freed. You'll also see information like the fault type and the access type. For example, a failed virtual address, translation on a read operation. There's also a resource history that shows details about the resource, including its size and whether it was marked as destroyed. After that, the GPU state section can tell you what the GPU was actually doing at the time. In some cases, this can give you a clue as to what part of the pipeline was active, such as texture sampling. If you need to dig into the shader itself, Aftermath identifies shaders based on code hashes, not file names, so you'll need to configure search paths in your shader binaries. In Unreal projects, the shader debug information is usually in saved/shader debug info under a folder that matches that target. This contains HLSL files and other metadata used to map crashes back to that specific shader code. But when have we actually used this in practice? Well, we had reports of a seemingly random GPU crash when using the editor, idling, moving the camera, unloading world partition, or performing editor undoing. The provided call stack and the GPU crash dump generated by NVIDIA Aftermath, which can actually be enabled by adding -GPU crash debugging, the command line, or setting r.gpu crash debugging to 1 in your project file. We could analyze that crash dump with NVIDIA Insight and allowed us to inspect the GPU's memory, registers, and other data at the time of that crash. And this led us to find that the cause of the crash was that a fragment shader was trying to access a resource that had already been destroyed, and thus resulted in a page fault error. So, when you're facing an issue, especially one that seems mysterious or intermittent, your best bet is to strip the problem down to just the systems that you're testing. Remove as many variables as possible. If you can replicate the issue in a clean, minimal test map or isolated module, you're far more likely to understand what's really going on. This also makes it easier for others, like your teammates or Epic support, to help. Another reason you'd want to do this is that if it's not reproducible or measurable, how do you know that you've actually fixed it? A fix that can't be verified isn't entirely a fix. You need to be able to confirm that the issue has actually been resolved to feel confident in deploying that update. This means having a baseline, applying the change, and then rechecking the data to ensure that the issue was truly addressed. So, we've identified the root cause of the problem, and that's a huge step forward. But now comes the next challenge, which is actually fixing it. Fixing a problem isn't just about writing code. It's about understanding the impact of your fix, making sure it doesn't cause new issues, or that it integrates well with the rest of the system. In this last section, we'll look at strategies and best practices to approach fixing problems effectively and safely, because identifying the issue is only half the battle, and delivering a solid fix on the problem is ultimately what matters. When it comes to fixing issues, it's important to understand that every fix has a blast radius. In other words, the potential impact or fallout from that change that it could have on other systems. Even the best intentioned fixes can unintentionally break other parts of the code base. So before making sweeping changes to fix a bug, it's best you assess the risk involved in actually making that fix. There's a few key factors to consider. The visibility, which is the issue or fix something that users or clients are going to directly see? The more visible it is, the higher the risk if something actually goes wrong. Complexity, how intertwined is this code or system that we're changing? If it's tightly coupled with heaps of other systems, even a small change could have big consequences that you might not be aware of. Do we fully understand how that system works? And if not, the risk increases because unexpected side effects become more likely. And lastly, timing. I'll be close to a milestone or a major release, because changes late in the cycle carry more risk since there's less time for us to test and fix those new issues. Understanding these factors helps you make smarter decisions about how to approach fixes, whether that means more testing, incremental rollouts, or involving more team members. So, when selecting how to fix an issue, it's crucial to align your strategy with the level of risk involved. For low-risk issues, where the impact is minimal and you have confidence in your fix, it's usually fine to just proceed directly, make the change, then test it thoroughly yourself to confirm that it fixes the behavior as expected and doesn't cause any side effects. But for medium-risk issues, where the fix affects more complex or visible systems, a more cautious approach may be needed. Make sure to perform thorough testing, and ideally have other team members review your changes or involve your QA team early. It's also important to document what you've done, as this helps track the change later on. For high-risk issues, where the blast radius could be large or the system is critical, it's best to apply mitigation strategies. It could be worth escalating high-risk fixes to your team lead or senior engineers to review, as their experience could help spot potential pitfalls in your solution that you might have missed. I would also consider maybe using feature flags or configuration toggles to control the rollout of that fix. It allows you to enable or disable the change quickly without a full release, which is very useful for managing risk in production. As I mentioned, some changes are relatively benign, while others have very visible user impacts. Player save data falls firmly in that later category. Modifying save structures post-release, in most cases, carries significant risk because it can significantly adversely affect user experience. So, in the example project in this case, we made 3 changes to a save system after the game had already gone live. Converting from string to a custom binary serialization with versioning, adding LZ4 compression to save files, and adding a code path that resaves all current user saves to enable compression on those files. Of these changes, few are as potentially catastrophic as that third change, as a failure in that process for any reason could result in the loss of any and all user data. So, by default, with the f-object name and string proxy archive, Unreal will serialize the save game as a string-like structure. This causes potential significant disk space overhead and may bloat your disk requirements. But the trouble was that the day 0 build had gone gold, with this method of serialization already implemented. So we could no longer guarantee that there was no user save data that would exist in this old string-like format. So, therefore, we needed to have a way to handle both formats in our save system. Luckily, the archive versioning system provides us a really easy way to do this. We reduced the overall save file size by, by 16.25% to 83.75% of the original size with this. And it could have been more, but there was a portion of the save data that we opted not to convert just due to the likelihood of introducing potential issues later down the line, as that data was not serialized on every load. Overall, this first change went pretty smoothly. We passed this to the QA team a few weeks prior to launch, and they tested it rigorously. This change went live early in the day 0 patch, so the majority of our saves would be this version in all later upgrades. But as mentioned, we could no longer actually guarantee that. Since we could not really fail saving due to this change, there wasn't much we needed to do in terms of fallbacks. We were just left with the need to test these changes heavily. But post-launch, it became clear that the current save size was an issue on some platforms that had limited cloud backup space. As we didn't want to convert the entire save to a custom format, we opted to explore compression. I can't go into platform-specific details in this talk, but it ended up being a bigger issue than simply cloud saves don't work. But our go-to was LZ4 for its fast compression speed, and as save hitching was actually now our primary concern when implementing compression. Unfortunately, the LZ4 compression natively in Unreal is actually LZ4HC at its maximum compression setting, which caused us upwards of 3,000 millisecond hitch. But it did attain a really impressive 14:1 compression ratio over the previous version. And on some platforms, this actually might have been fine if it could occur on a background thread, but for some of our target platforms that just didn't have enough physical cores for us to send this work to, it would lead to a 3-second game thread stall, which was obviously unacceptable for us, so we moved to a more standard LZ4 compression. LZ4's files are actually already in the engine, so getting access to the non-HC version was pretty simple. And the trade-off we paid was dropping from a 14:1 compression ratio to a 7.5:1 compression ratio. So it was about half the compression, but it still ran in under 50 milliseconds on the platform that was struggling with the game thread stall, so we took that as a win. So we now have vastly reduced the save size while minimally impacting performance, which is great. Except, users are going to already have saves made before this change, and they should upgrade seamlessly when they next save. But remember our cloud save issue. That's going to be an issue until a user manually replays every save that they've made. So, that led us to our last change, automatically resaving every save on every boot after the patch landed. This is by far the scariest of the changes we've made, as the blast radius of all these changes was fairly large, but this one is just plain gargantuan. If we got this unintentionally wrong, and failed to catch in testing any issues, we could break every save for every user on every platform. So, for that reason, we could not get that wrong. So, how did we do this? Firstly, we needed to make sure we identified what and where we could end up with corrupt data. These need to form the basis of where testing time was directed. Additionally, we added error injection to simulate potential failure modes during the resave, and a method to force resave on every boot during testing to maximize the amount of time that these code paths were being taken. Secondly, we needed to make sure that any error was as recoverable as possible, regardless of why an error has occurred. This includes assuming that our application may crash or lose power at any point during the process. So, to simplify the second front somewhat, we decided to handle upgrades by attempting to load the original save, generating a hash for that file, then deserializing it, and serializing it again to a temporary location. This temporary generates a checksum when serialized, so we could check that file for validity as well. We then loaded the temporary file, deserialized it, and compared it against the original save deserialized, and if they were valid, we would write the deserialized temporary back to where the original was. So, again, we loaded the original, deserialized it, compared it against the temporary file, and if they match, then we're good. We can go clean up the temporary data and rewrite the original save. This pattern allowed for us to recover from power loss, general data corruption, and save serialization logic issues. Admittedly, the latter would have led the game to being unbootable, but we would not lose any save data. Looking back at this, there were a few key steps that we could have made to make our save system even more resilient. Firstly, we could have used a staggered rollout, even for internal builds, to catch unexpected issues before they hit all users on that patch, and limiting the blast radius to a select group of users rather than all users at once. We could have built potentially more robust integration testing that simulated the full save load path, which would have been useful to help us catch breaking issues early. Ultimately, more time for testing would have always also made a big difference, but the game had already gone live. So, not just for functional testing, but specifically for platform-specific quirks, and especially around file I/O. I also just want to point out that sometimes the smartest fix is not another band-aid. It's a complete rethink. And I apologize to whoever I stole this off Google from. If a system is unstable, overly complex, or it breaks often, patching it again might just delay the inevitable. It's a sign that it may need to be refactored or rewritten, not just fixed. Quick fixes can feel productive, but they have the potential to add to long-term tech debt, especially if they're not properly tested. Instead, escalating the issue if a proper solution isn't possible right now, and being honest with the team about the real state of the system can be better. Not every project can afford a refactor, but when the cost of maintaining a system outweighs the cost of replacing it, it's time to stop applying band-aids and address the root cause. Even if you can't warrant a refactor, we always encourage within our studio to fix it as you touch it. And if you can't afford to rewrite a full system, you might as well just clean up something while you're looking at it, even if that cleanup is just better commenting parts of the code, so the next person that looks at it is looking at something a bit nicer. When you're making changes to a codebase or making commits to source control, please document your changes. Remember, it's not just for you. It's for the entire team, both now and for the development team in a few years' time when the context is long gone. That person might not know why that check was added or what caused a bug in the first place, so help them out. Just like the commit message I made up on screen, just be deliberate about your change lists. The second example has practically no explanation, no traceability, and no way to know if the crash was actually fixed or if the level stuff was even meant to be included. Just try to avoid vague commits like fixed issue or minor tweaks. Include the why, not just the what. Future you and your teammates will thank you. Cool. Okay, so this is the last point that I wanted to quickly touch on, and one that we come across pretty often in projects that we help out with, which is modifying the Unreal Engine source code. Depending on the issues you face, engine modifications can be the right move, but they often come with trade-offs. You just need to be mindful that every new Unreal Engine version introduces potential merge conflicts, and that can mean hours or even days of manual work to integrate upstream changes. It also creates friction for your whole team, and onboarding new engineers can become harder. But when is it justified? A critical bug fix that isn't yet merged upstream and is blocking you, a core engine limitation that is in your way of your game's essential feature, a proven optimization, one that gives you real validated performance gains, or if you're committing to a long-term engine fork, like a console fork or an internal tech platform, where you'll own the custom version over time. But even then, I'd recommend following best practices. Start with a plugin or an engine subsystem if at all possible. Try to only modify base engine files if it's actually necessary. Try to isolate changes into new files if possible, or dedicated classes. Try not to scatter them just randomly throughout the code base. Document every change. Keep a change log and include the reason why you had to modify the engine in the code comment. And I recommend maintaining a clean mirror branch of the release Unreal version so that you can compare diffs and it will help you with merging. And lastly, if you're working with source, seriously consider Perforce. Git can work, but pretty much all of Unreal's source control tooling is with Perforce in mind. And that makes this workflow just way more manageable. Cool, that's it. Thank you all so much for joining me here today. I hope this session gives you a bit more insight into the process that we take at Prismatic when tackling tricky Unreal challenges, and maybe even give you a few tools or techniques to take back to your own team.
All right, hi, I'm Jack. So I'm a game programmer. I want to ask, like, in terms of problem solving. Also based on your the problem you face. Some of them require more time. How do you given that your time is your restrictions, how do you tackle those problems?
How do we time box a solution?
Yeah,
that's a really good question. In terms of how our studio operates, we look to time box an issue before we take a card. So, for example, on Jira, we would look to allocate a time that we would be willing to spend on looking to, try and fix an issue before we try to elevate it to further members of our team or to maybe reach out to Epic in some cases. So what I would really recommend engineers that are developing their skill sets to do is start trying to time box yourself. Maybe you can even put it on the card if you've got project management systems in your studio and things as well. And try and keep yourself to those times. Eventually you'll get better and better and better at refining how long you think, just based on your gut feel, you think problems might take. Okay. For two reasons. If you reach that maximum, you know that you're kind of at a stage where it's worth elevating to somebody else. You can kind of back yourself that if it was a simple thing, you probably would have solved it in the the amount of time that you initially budgeted yourself. So there's no kind of silver bullet, but what I would recommend is don't spend forever on a problem. Don't just keep banging your head into it, because that's ultimately going to cause more damage, especially to your your production roadmap, especially if you spend a lot of time on something. So I'd recommend, when you take an issue, try to conceptualize how difficult you think the problem might be to fix. Time box yourself. If you reach the end of the time box, then I'd like to elevate that to production staff or lead engineers or senior engineers.
Okay. Thank you very much.
No worries.
Hello, thank you. I just want to ask about how the compression of the safe game system implemented. Do you modify the engine code, or it is your custom? Is it your custom safe game system?
No, we actually didn't have to modify the engine source. I believe for the save system. Keegan, nod head or shake head. Yep, we didn't have to. I think that again, my recommendation for any team is to try to do it without modifying source first. We did, and we managed to get around it. When I say it was already in the engine, what likely that means is that we just duplicated it into our own system or plugin. And I'd always recommend that to people. If you're finding something that exists in the engine and it's locked away, just base your solution off it. Copy it into your own plugin, work away at it, leverage the engine systems that already exist. And that's how we built around our save system.
Okay. Okay, thank you. Because in our project, we have been hit with about 2 gigabytes of safe game system.
If you'd like to chat about it further, I'm going to go to the dev lounge after this so we can have
Okay,
have a talk.
Thank you.
Cool. Got a few more minutes? Anyone else? Yeah.
Hey, great talk. Really enjoyed it. Just wanted to, well, 2 questions. First one was you showed off some interesting profiling techniques and performance techniques. Have you used Superluminal as well?
I personally haven't, but that's not to say that our team hasn't.
Yeah.
Typically, when we're, well, at least when I myself am approaching new profiling tools, I always find that it's always a little bit of a unique toolbox among the engineers in your team about what other people have used at other studios or at other software companies as well. You know, for example, the tools on screen were things that I myself hadn't actually been exposed to until about a year or so ago, when other members of my team were showing use cases of when they were bringing in their experience with these profiling tools. So what I would really recommend is just when you are exploring new tools, or if you have experience that you know that other engineers in your team might not have experience with, it can just be worth sharing that information and explaining not just how to use the tool, but I find way more interesting and important is why have I picked this one? Out of all the different examples, why have I picked this tool? Because that gives people confidence to try that tool themselves. You know, it's one thing for me to show you how to print out a mem report, but I think that until you have the opportunity to experience it yourself, like if you're running into a situation where a static memory output would be really valuable for you, then having that as like a tool in your kind of kit to be able to be comfortable bringing out, you know, that's how we always try to encourage it within our studio.
On that note, actually, in terms of encouraging it at your studio, do you have any sort of cultural practices or anything like that that you guys adopt?
Oh, we just have very in-depth stand-ups sometimes.
Yeah.
Most of the time, it's pretty much that one of our engineers will come and be like, hey, look, we're working on this crazy complex thing. I had to whip out something that I haven't used in, you know, a year or two. And then that's just interesting to the rest of the team.
Yep.
And then sometimes, but based on that, if there's enough interest in us wanting to actually skill up on that, then we could definitely put some support around that person to, you know, be able to showcase that tool to the studio further. You know, for this talk, for example, not all of our team had used Pix or had used NVIDIA Insight to Math and things like this. So this became a really good opportunity for us to explain the wider use of these tools beyond just the specialists in our team that felt comfortable using them.
Sure. I got some more, but I'll give someone else.
We'll chat in the dev lounge.
Yeah.
I'll be in there after this. Cool. I've probably got time for one more.
Hello, good afternoon. I would like to ask, do you have any tips regarding checking the GPU crash on Xbox Dev Kit? Because sometimes during play
Do I have any pictures to share?
tips?
Tips.
Yeah.
Look, unfortunately, I'm not allowed to share that in this talk because I believe that would be covered under a platform NDA. But if you'd like to reach out after the talk and we can confirm that NDAs are in place on both sides, I might be able to share a bit more information about that.
Right, okay, thank you. But the second question is, can we run NVIDIA Aftermath on non-NVIDIA hardware?
Sorry, can you repeat the question?
Can we run NVIDIA Aftermath on non-NVIDIA hardware?
That's a good question. I will double check that. If you want to come to the dev lounge, we can chat about that as well.
Okay, thank you very much.
No worries. Cool, thank you so much. Look, if anybody's, okay, last slide's not up there again anymore, but if anybody ever has any problems that they're running into, we really want to support, you know, industry in our region. So our website's prismaticstudios.co.nz, contact@prismaticstudios.co.nz. Feel free to get in touch. We'd love to help. And also, if anybody's looking for work in New Zealand, potentially Australia, we're going to be hiring pretty soon. So keep an eye out. Thank you.